So it's my great pleasure to introduce our next speaker, who is Andrea Solotar from the University of Buenos Aires, and she will talk about Hahn's conjecture for bounded extensions.
Okay, thank you all for the invitation. So I'm going to talk about joint work with Claude Cibils, Marcelo, Lanzilotta, and Eduardo Marcos that appear precisely today in the archive. So you can see the details there. So my talk, will be about finite dimensional algebras. Nevertheless, some of our results are for also for infinite dimensional algebras. But it's simpler to talk about finite dimensional algebras today. And it's about Hahn's conjecture. Hahn's conjecture is a subject on which we have been working for quite a long time. And it relates to homological invariance of A. From one side, the global dimension that you can see as a geometric invariant. And from the other side, the Hochschild homology. The conjecture precisely says that A is smooth. By smooth, I mean finite global dimension, if and only if the Hochschild homology stops at some point. Okay. So if you look at the right-hand condition, on the right-hand side, the Hochschild homology, in fact, Keller proved that for finite dimensional algebras, if it stops, it's only different from 0 in degree 0. Okay. And for this, he uses Hochschild and cyclic homology. So our one inspiration may be the commutative case. In the commutative case, it is known that the result is true, and it has been known for a lot of years, many years before conjecture was explained, was done by Hahn. And in the Hochschild, in the commutative case, you have that there is a decomposition called the Hodge decomposition of the Hochschild homology in degree n. You can decompose it in n parts. And the last part is the exterior power of the Carrier differentials. And the first part is the Harrison homology, and also it's isomorphic to the André-Quillen homology shifted by 1. So André-Quillen homology has one property. It satisfies what's called a Jacobi-Zariski long exact sequence, which is mainly a change of rings sequence. Okay, and the annihilation of the André-Quillen homology is closely related to smoothness of the algebra, because in fact, if A is smooth, in the commutative case, there is only one summand here, which is the last one, that survives. And this is the Hochschild-Costan-Rosenberg theorem. But in the non-commutative setting, there is no André-Quillen homology. There was no Jacobi-Zariski sequence. And but finally, Kai-Gun some years ago proved that there is a kind of Jacobi-Zariski sequence for an extension of K algebras, but asking A to be B flat. Okay, but for us, this hypothesis was too strong, so we started thinking about possible generalizations. So let me explain that the idea that we have is that we want to study the smoothness of a certain algebra, finite dimensional algebra. And there is a lot of arrows and relations that just cause some noise, okay? And we want to get rid of them. We want to keep just the part where there is the problem, okay? Because the singularity, as in the commutative case, happens somewhere, okay, so in some precise place. So we want to get rid of all the rest. Okay, so we have been working on this, and we have recovered Jacobi-Zariski long exact sequence in some cases involving Hochschild homology and relative Hochschild homology. And in some cases, it's not so exact. We'll see it. And then we prove that if we have B as a subalgebra of A, and the extension is what we call a bounded extension, that I will define now, then A satisfies the Hahn conjecture if and only if B does. Okay, and the conditions to be a bounded extension is that, well, you have B, which is inside A, and you have a quotient, Well, this quotient is a B bimodule, and this bimodule has to be B tensor nilpotent. The tensor products over B should stop at some point, should be 0. And then it must have finite projective dimension, and it has to be either left or right projective as B model. So this is a bounded extension. And we have several examples of bounded extension. And let me mention our main tool, one of our main tools, which is the relative Hochschild homology. Relative Hochschild homology was defined long ago by Hochschild, but was not used and were found, but here we have used it a lot. So you have an extension of algebra, of K algebras, and you can define the exact category of A modules respect to split exact sequences. And I have a problem with my internet connection, sorry. And there are enough relative projective modules, and so we can construct relative projective resolutions. And then what is this? These are relative projective A modules, and we have a differential, and there must be a B contracting homotopy. So from this, we can define the relative Tor, and the Hochschild homology is going to be a relative Tor with respect to the respective enveloping algebras. Okay, so we constructed, if you have to compute a Tor, you need a good resolution. So we have constructed a reduced resolution, and this reduced resolution has in the middle these quotients, these B bimodules A over B. And this is kind of a generalization of what happens when you take the tensor product over the semisimple algebra KQ0. But in that case, it's easier because you have the algebra is split, and then, well, this saves you a lot of problems. Because the problem here, the main problem is that this quotient has no multiplicative structure. So you want to define the differential, and for this, you need to choose a linear section of the projection of A into A over B, and then this linear section appears in the differential, and each term of the differential separately is not well defined, but the whole of it is well defined. And finally, the differential does not depend on the linear section, on the choice of the linear section. So with all this, if A over B is B tensor nilpotent, then Hochschild homology, relative one, and relative Hochschild cohomology annihilate. Okay, so we continue having an extension, an A bimodule, and we get a Jacobi-Zariski that we call long nearly exact sequence, meaning that in two of each three terms, there is exactness, but maybe at the terms corresponding to the Hochschild homology of A, there is not. So, but we manage, we have spectral sequences that tells us what happened, that tell us what happens. So with these conditions, we have that A satisfies Han if and only if B does, and this has two things to prove, one about Hochschild homology and its annihilation, and one about smoothness. So for proving each of these, we need different hypotheses. The B tensor nilpotent is for both of them, and for one of them, we need, for the first one, we need the finite projective dimension as B bimodule, and for the other one, we need to be projective on one side. So in fact, we can ask ourselves if there are bounded extensions, and in fact, there are a lot of bounded extensions, and we have given conditions for the extension to have tensor nilpotency and to have finite projective dimension. Well, this is okay if we start with V smooth, and to have that when we add arrows and relations, we keep the projectiveness on one side, okay? So roughly speaking, and I'm going to show you an example in half a minute, we have to have what are called interrupters in the new cycles, in the new relative cycles, and some conditions on the relations we add. So let me give you this example. We have B is the algebra with quiver in black, and the relation that if you go first like this, first like this and then like this, it is 0, and then you add the arrow A and you add this relation, and then you have a cycle in principle here, but it can be reduced to something in which was already in B. So this we call an interrupter. And also the relation we add has one branch that starts with an element which is a new arrow. So in this condition, in this situation, we can assure both tensor nilpotency and the projective, being projective on one side. Okay, so this allows us to enlarge a lot the family of algebras that we can consider with this for the Hans conjecture, because we are no longer considering split extensions. And so we want to continue simplifying our algebra. Thank you very much.